So we are going to start session on chi-square. So now 3 sessions will be on the chi-square, and there will be chi-square test of goodness of fit, chi-square test of association, and chi-square test of two proportion. So after these 3 sessions, we'll go to the breakout room for the chi-square. Could you all share your screen apart from, I think I've heard few candidates or the participants who could not open the data, I guess. Maybe we'll look into that matter, why there was an issue with the opening of the data. Then again, you can try in the second breakout room. And it is a request from the mentor, those of you who could share the screen in the first breakout room, kindly encourage the others who could not share their screen in the second breakout room. So they should be given the chance first, who could not share their screen in the breakout room in the first instance. So this chi-square test of goodness of fit, again, we'll see this under the following headings. We'll see the basic concepts of this chi-square test of goodness of fit, the research question, then assumptions and hypothesis, what are the commands and interpretation, and at last we'll summarize the commands. So this chi-square test of goodness of fit, basically it tests the distribution of the case in a single categorical variable. So in this case, you have got only one variable and you see whether it follows a distribution or not. That distribution can be a known distribution. In that case, it will be unequal. If the distribution is not known, you take the hypothesized distribution, which is the equal distribution. And all these three concepts, this we call at a single sample non-parametric test, which is the chi-square goodness of fit test. Suppose, for example, if I say that the prevalence of obesity is 5% in Indian children, that means I did a study and I found out that there are 90 children in my study. So based on the prevalence of India, I would expect that out of 90, there would be 18 cases of obesity. But there are 25 cases of obesity in my sample. So I just want to know whether this number is significantly higher or than the expected or not. So the research question in such scenario will be, I want to know whether the proportion of BMI categories of MBBS students of the college differs from the national proportion or not, whether the surgical site infection rate of your ward is different from the overall surgical site infection rate of the hospital, or whether the passing percentage of your college is significantly higher than the minimum desired percentages. So in all these research questions, what have you observed? So you have seen that there is a single variable and we want to test the proportion of that categorical variable against a known proportion or against a hypothesized proportion. So the test of choice in such case is the chi-square goodness of fit test. We call it as a chi-square goodness of fit because we want to know whether the data or the variable which have, how it is fitting into against a known or a hypothesized proportion. And it is also known as the one sample chi-square test. So there are three basic assumptions of this test. First assumption is there should be one categorical variable, and that variable can be a dichotomous variable or a polytomous variable. A dichotomous variable is a variable where you have got two categories, like gender, male and female. It is a dichotomous variable. Presence and absence of diabetes, two category. It is a dichotomous variable. A variable can be of polytomous. That means it has got more than two category. Maybe socioeconomic scale, mild, lower, middle and upper. Disease severity, mild, moderate, severe. Or blood group A, B, B and O. That is again a polytomous. So if you have a categorical variable which has got more than two levels, that is known as the polytomous. The second concept is the independence of observation. Now, what is this independence of observation? That means if there are two categories, in this case, like for example, if there are three categories and if you have counted one person in one category, you will not count that person in the another category. Suppose if you are examining 100 patients for a type of blood group, if you have counted means third individual as A, then you will maybe A blood group, then you will not count that person maybe for the other blood group. Usually that's a study design issue, and if you ensure the separate participant in each group, this assumption is met. And the third assumption is the expected frequency of the cell. It should be at least 5 in each group, and that we call it as a third assumption. And this expected frequency, we'll see what is this expected frequency. And in chi-square, we always talk of this term expected frequency and the observed frequency. So this chi-square goodness of fit test, it compares the observed frequency in the categories with the hypothesized frequency. So we may have two conditions. The hypothesized proportion, it is available. In that case, we enter the hypothesized proportion. If the hypothesized proportion is not available, we assume that it is of equal proportion depending on the number of levels. So if there are 3 levels, it will be a 33.3, 33.3 and 33.3 in each category. If there are 4 levels, it will be 25% in each category. So we assume it to be of equal proportion, and we'll see in JAMOVI how we do that. Suppose we have recruited 100 individuals in our study to know whether the proportion of normal, overweight or obese categories of children is significantly different from the hypothesized proportion. So in this case, if the hypothesized proportion is like, I have this proportion 50% as normal, 40% as overweight, and 10% as obese. But if the hypothesized proportion is not available, then I will take each of three as an equal proportion of 33, 33, and 33. So this is the example of a known proportion or a hypothesized proportion. So now let's see how we can do this. So I'll show the question. So this is the question for the goodness of it. So I would like to understand whether the proportion of various disease severity of COVID cases admitted in the hospital follows the same proportion as those at the national level, where it is known at the national level, 20% of the patients are severe, 20% are moderate, and 70% are asymptomatic or mild. So this is the first question. And the second question is, I would like to understand whether the proportion of male and female COVID cases reported in my district follows the same proportion at the state level. But at the state level, it is known that the 40% are females and 60% are males. So I'll go to the data set. So data set for this is the .omv file you can see. So .omv file says that this is the JAMOVI file. So this is the demo sheet for me and the other sheet is for you. So for workshop purpose, we have created separate data file. Although the data is, we have this data as a single place, but we have split, we split this data set just to ease out the things and just to have a better, so that if there are many variables, you will be confused seeing those variables. That's why we have reduced the number of variables for each data set. So this is the data set. So now the research question is that I have to test against the mild, moderate, and severe, like mild, asymptomatic, and moderate and severe. So for the option of chi-square goodness of it, you will use this option of frequencies. So go to this frequency. In this case, you can see that there is an option of chi-square goodness of it. So click this option. When you click this option, you can see there is an option of variable. So we know that we are only testing single variable. So single variable, it is the variable of the outcome, that is a severity. So this is the disease severity variable. I have shifted this variable. And now you can click on this expected count, because you know that expected count should be more than 5. And in this case, you can see the expected proportion. So if you have not given any value, it will take it as an equal proportion, what we learned. But now I know that 60% of the cases were asymptomatic, 30% as moderate, and 10% as severe. So with that, I may enter this specific value. So the values are 60% of the 70% are asymptomatic. So this is the 70%. Sorry, it was 70%. So I'll enter 70. This is 20. And in this case, it is 10%. So if you see this 10%, now it is against a known proportion. And in this case, you can see here, this is the expected frequency. So expected frequency in each cell, it was in one cell, you can see that expected is 1.98. So in this case, you can say that one cell is having expected cell frequency less than 5, but otherwise in all the other two, it was expected cell frequency was more than 5. And the chi-square, this thing is significant goodness of it, and this is 0.001. So you can say that the proportion, and you can have this, the proportion. So proportion is 68.9% was asymptomatic, and the 19.4 was symptomatic, that moderate, and 11.7 were severe. So there was a difference, and you can say that this was the expected. So expected was 70, 20, and 10, and observed was 68.9, 19.4, and 11.7. So similarly, you can write the interpretation. So how you will write the interpretation? So this is the dummy table. The dummy table you can take directly. So this was for the chi-square test of association. Goodness of it, like in this case, you can write that these participants are same proportion. You can write that these many peoples were of X, these many of Y, and these many of Z. And since there are only one assumption in this case, that the expected cell frequency. So you can write that expected cell frequency in one cell, it was less than 5. So this was for the chi-square test of goodness of fit. Now coming to the second example. So second example was I have to test for the gender. So gender was like 60 and 40. So if I shift gender in this case, so I have to, the state was showing that 60% are male and 40% are female. So I have shifted these variable here. Again, I'll change this 40% as females and 60% as males. And I expected count, you can say that expected count, it is 175 and 4.39, and this is 27.8 female, and this is 72.2. So this and this was significant.